Hello everyone. In this video I will be going over my solution for the problem named Elsa's fitness and the luxury number. This problem is an excellent problem which will teach you the applications of divisibility and brute force algorithms. So in this problem we are basically given intervals L, R, and we want to find out the number of luxurious elements in the range L to R. So a number is called a luxurious number if it is divisible by the floor of its square root. So first let's understand what this function, the floor of the square root, does. So let's take a few examples. Let's say that the number is 8, then clearly 2 square, which is 4, is less than 8, and 3 square, which is 9, is greater than 8. That's why you can see that 8 is sandwiched between 2 square and 3 square. So the floor of 8, the floor of the square root of 8 will be 2. Similarly, the floor of the square root of 56 will be 7, because 56 lies between 7 square and 8 square, which is between 49 and 64. And when the number is a perfect square, that time you will take the square root as it is. So 100 lies between 10 square and 11 square. So that's why you will just take 10 square. So the square root of 10 square is 10. And these are the values of square root of x floored. Now we want to find out numbers such that they are divisible by their floor of the square root. So all such numbers are called luxurious numbers, and we want to find out how many such numbers exist between the two values of L and R, where L and R can be up to 10 power of 18. So obviously the first idea which comes to mind is the Naïve brute force, which is to just go for each index I, for each number n, let's say. So for each n in the range L to R, you just check whether n percentage square root of n percentage square root of n. So square root of n will by default give you the floor of the square root of n. In C++ or in Python and Java, you can just typecast it into an int, and if n percentage square root of n is 0, we'll just increase the answer by 1. So answer plus plus, and in the end you just print answer. So this is the very naive brute force, and for the first few sample test cases it will work. So if you consider the third sample test case, then you can see that 119, 120 and 121. So let's look at those three numbers. Let's look at 119 first. We know that 119 square root floored will be, so 10 square is 100, 11 square is 121. So it lies between 10 square and 11 square, which is why it's 10. Now the square root of 120 is also 10, and the square root of 121 is 11. So that's why when you consider these three numbers, we can see that 10 does not divide 119. So this is not counted. This is counted because 120 is divisible by 10, and this is counted because 121 is divisible by 11. So these are the two luxurious numbers. That's the name given in the problem statement. So that's why we will print that there are two luxurious numbers in the third test case, and you can read the explanation for the first test case. These are all the luxurious numbers. You can verify them by hand. Now let's try to come up with the key observations for finding out which are the luxurious numbers efficiently, because obviously this is an O of n algorithm which will basically time out when n is up to 10 power of 18. L and R are up to 10 power of 18. So let's try to develop an efficient idea. So the efficient approach for finding luxurious numbers relies primarily on the definition of a luxurious number, which is that the square root of the luxurious number should be a divisor of the luxurious number. So this symbol is the symbol for a divides b. So square root of x is a factor of x. That is the notation which we will use for divisibility. Now we want to ensure that square root of x is a factor of x, except for the twist that it's not necessarily a perfect square. So if x is a perfect square, then obviously square root of x will be a factor of x. If you take any perfect square, 144 for example, 12 square is 144, so 12 does divide 144. However, when the number is not a perfect square, we want to ensure that this weird symbol, the floor of the square root of the number, is a factor of that number, and this is where the complications arise. So let's try to find out an easier way to think about the floor of the square root. So the easier way, which I used from the very beginning of the video, was that the number x should lie between two perfect squares. So let's say x lies between k square and k plus 1 square. Now in this case, we know that if x lies between k square and k plus 1 square, then the key idea, this is the most important step in our solution. It's finding out the value of the floor of the square root of x, and the value of the floor of the square root of x is basically k. So if you consider any of the examples which I illustrated in the samples, you will see that whenever we sandwich the number x between two perfect squares, then the floor of the square root of x is the smaller perfect square, so it's k basically. And now we will build on this key equation for basically figuring out how we can use this equation in simplifying our counting. So we want to still count the number of luxurious numbers in a particular range. So first let's try to find out the condition for luxurious numbers. So we know that the condition has now reduced to k should divide x, where x lies between these two perfect squares. So another way to think about this is that for all x, so instead of saying that given an x you find the value of k, an easier way to think about this is given a particular value of k. So given a particular value of k, we can go for each x in the range k square to k plus 1 whole square minus 1. So for each x in the range k square to k plus 1 whole square, so k plus 1 whole square should not be included, so we'll put a round bracket to signify that k plus 1 square is not included, or you can just say it's k plus 1 whole square minus 1. So for each x in this range, we know that we want to basically, we know that the floor of any x, the floor of the square root of any x will be k. So given k, we can update all these values of x. And how exactly do we find out which x satisfies the divisibility condition as well? So just to summarize what I've done so far, in case it's getting confusing, what we have basically established is that the square root of the floor of x will be k, where k square is less than or equal to x is less than k plus 1 square. And we also know that if you reverse this thing and if you basically choose a particular value of k, so if you choose k is 12 for example, then for each number in the range 12 square, which is 144, till 13 square minus 1, which is 168, for each k in this range, we know that, so for each x in this range, we know that the floor of the square root of x is equal to 12. This is basically all I've said so far. The floor of the square root of x is k for each x in this range given a particular value of k, and we will be using this in counting how many luxurious numbers exist, because if you look at these two numbers in the range, if you look at the numbers k square and k plus 1 whole square minus 1, you will realize that both these numbers are divisible by k. So k divides k square, or k square is a multiple of k, and k also divides k plus 1 whole square minus 1. So this means that if you want to find out how many x are there such that k divides x, then you can just find out how many multiples are there. So we know that k square is k into k, so this is the kth multiple of k, and we also know that k plus 1 whole square minus 1 is basically, you can do the math, it's k into k plus 2. So we know that there are essentially only 3 multiples of k in this range of the values of x. So it's k into k plus 1, or k into k plus 2. So the left boundary is k into k, the right boundary is k into k plus 2, and the number in between is k into k plus 1. So therefore 3 values of x satisfy k divides x, where k is the floor of the square root of x, and that's how it connects back to the original problem statement. So this basically means that we know that for each value of k there are 3 values of x. So for each k there are 3 values of x, specifically k into k plus 1, and k into k plus 2. You can also verify that k into k plus 3, for example, will have a floor of square root of k into k plus 3 greater than k. So that's why only these 3 values satisfy both the conditions. So these satisfy both the conditions. The first condition is that the floor of the square root of x should be k. This is the first condition. And the second condition is that k should divide x. So there are only 3 numbers which satisfy these 2 conditions both. And now what's basically is left is to figure out all the possible values of k, and we know that for each value of k there are going to be 3 values of x. So basically we need to go through the values of k in this interval and figure out in each interval how many k's are there, and for each k we know that there are going to be 3 values of x. Now the tricky part in the final ending is to figure out the values of k which lie between L and R. So notice that L and R need not be perfect squares, and there's no special property. So this is where it gets a bit tedious, because after doing all of this work and after realizing that the answer should be 3 times the number of values of k, you actually need to check border cases as well, in addition to just finding how many such k's exist. So now I'll be explaining how we can do that. So returning to the samples, let's understand how we can calculate the values of k. So let's take the range 8 to 20. We know that in the range 8 to 20 we are considering the values of k. The lower bound of k is basically the square root of 8. So we know that the square root of 8 is 2, and the upper bound is going to be the square root of 20, and the square root of 20 is approximately 4. Now we know that for all the elements in this range, so if you consider the range 2, we know that for the elements in the range 2 into 2 to 2 into 4, so for all those elements in the range 2 into 2 to 2 into 4, so 2 square comma 2 into 4, which is basically the range 4 to 8, the condition will be met. So there are precisely three numbers, 4, 6 and 8, for which this condition is met, that the square root of 4, the square root of 6 and the square root of 8 have their are factors of 4, 6 and 8 respectively. And we know that in this case, in the upper bound, we know that 4 square for all elements in the range 4 square to 4 into 6, which is basically the range 16 to 24, there are going to be three elements. Those three elements are 16, 20 and 24, which satisfy the property that the square root of the value of that number is a factor of the number. So given this, we know that these form the borders, because 20 lies on the border and 8 lies on the border. So these are tricky cases. So for simplicity, we can just first consider the boundaries to be the square root of L plus 1 to the square root of R minus 1. So this basically means that the boundaries for K will be 3 to 3. So initially let's just consider K to be 3 to 3, and once we fix the value of K to be 3 to 3, we know that all the values when K is 3 to 3 satisfy the condition that the square root of the square root of x is a factor of x itself. So basically what I'm trying to say is that if you consider the lower bound to be square root of L plus 1 because we want to ensure that it lies within the range, and if you consider the upper bound to be square root of R minus 1, and if you want to be more conservative, you can take a bigger number. You can take square root of L plus 6 for example, because that will and square root of R minus 6, because that will make it crystal clear that K square and K into K plus 2 will lie strictly within the range L to R, because it's clear that over here if you consider R minus 6 whole square, then obviously that will be much less than R, and that's why this is a safer bound, where you take the lower bound to be square root of L plus 6 and the upper bound to be square root of R minus 6. So in this case, we know that for each x, so for each k in lower bound to upper bound, there are going to be three values of x. There are three values of x, and that basically means that we can just use the number of elements in the range lower to upper. So the number of elements in the range lower to upper is upper minus lower plus 1. So we can use upper minus lower plus 1 as the initial value of upper minus lower plus 1 into 3 as the initial value of answer. So the answer is initialized to this, and now once we have figured out that the answer is this, we can check for the border cases. So I'll just show you this part of the code, because the code is actually short, but there are many steps in the solution, so don't get demotivated. The code is actually quite neat. First, let's look at this part of the code. So we know that this part of the code basically has, for each test case, taking the value of L and R and taking in lower to be square root of L plus 6 and R to be upper to be square root of R minus 6. You can keep it as 3, or you can keep it as really any number, as long as you know for sure that R square will be less than R, and R into R plus 2 will also be less than R, and that works for that works for the upper square root of R minus 3. So that's why lower and upper is initialized to this, and answer is 3 times the number of values of k in that range. Now the border cases. So for the border cases, we need to go for each remaining value of k. So for each value of k, which is uh, which is basically between lower and L, and basically for each value of k in lower to lower minus 6 to lower minus 1. So lower minus 6 basically means that for a smaller number, so lower is square root of L. Notice that lower is square root of L plus 3, which means that this means that we may miss square root of L. We may miss k is square root of L, and k is square root of L plus 1, k is square root of L plus 2. We may miss some of these values of k. We are taking only the values of k which are below square root of, which are above square root of L plus 3. So that's why we need to iterate for all values from square root of L minus 3 to square root of L minus 1. So basically lower minus 6 till less than lower. Wherever lower starts, we know that for sure k square will be greater than L. So that's why it will lie within the range of L to R. And we know that these values of k we need to check. So we need to check for each k in this range, if both the conditions are satisfied. So the two conditions are, the first condition is that the number should be between L and R. So I've put that over here. I've put it in a function lies between L and R. It basically returns true if x lies between L and R, and false otherwise. So given this function, we can use that to efficiently check whether k square lies between L and R, or k into k plus 1 lies between L and R, and k into k plus 2 lies between L and R. So these are the three values of k, these are the three multiples which we know can lie between L and R and also satisfy the condition that, so these three values of x should be divisible by k, and we just need to check whether they are in the range L to R. So we do that using the function lies between L and R, and if both the conditions are met, we insert this value of x into a set to check duplicate elements. So a common mistake which you will encounter is overcounting the border values. So to solve that problem, you just put all those elements into a set and find the size of the set, and once you do that, you will know these are the distinct elements which lie on the borders, so you don't need to worry about border cases anymore. And this is for all values less than lower. Now for all values greater than upper, so for all k greater than upper, up till some reasonable value, so this could be upper plus 3 as well. It doesn't really matter what these values are, as long as they are like big enough. 3 to 5 to 10 should be enough. Basically we are ensuring that all the borders are accurately scanned. So we know that if we are checking for each value of k in the border, we need to again ensure that both the conditions are met. It should lie between L and R, k square should lie between L and R, or k into k plus 1 should lie between L and R, or k into k plus 2 should lie between L and R. And each time we encounter a particular value of x which lies between L and R, we insert that into all. So all stores all possible border values of x which can satisfy both the conditions that x lies between L and R and x is divisible by its square root. So once you store all these border values, you will just increase the answer by the size of the border values, and initially answer is initialized to all the middle values. So it's 3 into the number of values of k plus all these border values, and these border values can be very tricky, so you may need to pause the video or you may need to come up with your own solution for accurately scanning the borders. I did this way, maybe there's an easier way, but this is the key idea for the entire solution. So you can verify that this code gets accepted. I hope you like this problem and my solution. If you have any doubts in any part of the solution, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. Thank you.